So to summarize, you compute an by taking 1 over t. Sorry. So you compute an by taking 1 over t, integrating 0 to t, x of t e to the minus j, and omega naught t dt. Okay. Now, since x of t is periodic with period capital T, and so is this complex exponential, since both of these are periodic with period capital T, it doesn't really matter, right? When you integrate over one period, it doesn't matter where you start and end as long as it extends over one full period. Okay? So if you have a periodic signal, right, it doesn't matter, where you start and end this integral as long as it covers one period. Okay? So sometimes we write it more generally as 1 over t, the integral with this subscript capital T to indicate that you're integrating over one period of capital T, okay, no matter where you start from, of x of t e to the minus j and omega naught t dt. Okay, so this thing here indicates any interval of duration t. Okay? Now, if you've taken a class on linear algebra, okay, if you've taken a class on linear algebra, then you should have more insight of what we're doing here, okay? So in linear algebra, you can view this as taking the inner product between x of t and the basis function e to the j and omega naught t. So you can view this as the inner product between x of t and the basis function e to the j and omega naught t, okay, or often denoted by this bracket here. Okay? So you can view this integral here as taking the inner product between x of t and this function e to the j and omega naught t. Okay? So when you take the inner product between complex functions, you often take the complex conjugate in the second term. Okay. So the inner product gives you the projection of x of t onto projection of one function onto the other, right? So geometrically, this is like having a vector x of t here, a vector e to the j and omega naught t here. And when you compute the inner product, you're computing the length of the projection onto this direction, right? So intuitively, what this gives you is the portion of x of t. What an gives you is the portion of x of t projected onto this direction, e to the j and omega naught t. Okay? So this AN measures the portion of x of t in the nth harmonic component. Okay, so AN measures how much x of t lies in the direction of the nth harmonic component. Now, from this derivation here, this is basically the inner product between e to the j k omega naught t and e to the j n omega naught t. Okay. So this expression basically tells you that each one of these complex exponentials are orthogonal, okay, because they are 0 whenever k is not equal to n, right? Their projection onto each other is 0, right? So you may have another complex exponential, let's say in this direction, that's e to the j k omega naught t, where k not equal to n. Okay? So what we're saying here is that we can represent x of t as a linear combination of these complex exponentials. And the coefficients here should be the projection of x of t onto each one of these directions, right? So we find here a n, and then we find here a k, right? So x of t would be a n times e to the j n omega naught t, and plus a k times e to the j k omega naught t, right? But imagine that this goes to infinite dimensions, okay? Okay. So you view this as linear combination of orthogonal basis functions e to the j k omega naught t for all k. Right, so if you've taken a course on linear algebra, right, then the insight for this is clear, right? So the insight for this is just to say that we can represent any periodic signal using the set of bases formed by harmonically related complex exponentials. And in order to find the coefficients, ak, right, we need to find the projection of x of t onto each one of these directions. Right? So what we're doing here is taking the inner product of x of t with this basis function e to the j n omega naught t, and this inner product requires you to take a complex conjugate of this second function, right, instead of its original form. Okay. So if you haven't taken a course on linear algebra, then just keep this in mind so that when you do take that course, it'll bring you further insight. Okay? Right, so in summary, right, if x of t has a Fourier series representation, right, x of t is a superposition of ak e to the jk omega naught t, where ak is just the integral of x of t times e to the minus j k omega naught t, 1 over capital T, okay? Right, so these AKs, as we mentioned, is called the Fourier series coefficients, or sometimes called the spectral coefficients of x of t, okay? And the reason you may also call it spectral coefficients is because AK is the coefficient corresponding to the spectral component at frequency k omega naught t, okay? So it specifies how much of the frequency component k omega naught t is contained in the signal x of t. Okay, so any questions up to this point? Okay, if not, let's look at an example. Okay. So in this example, we have a periodic square wave, right? So we have this square wave from minus t1 to t1, and it is repeated every integer multiple of capital T, okay? So if you look over only one period, from minus t over 2 to t over 2, then x of t is essentially this, right? It's equal to 1 from minus t1 to t1, and 0 for the remaining period. Okay. So this is over one period minus t over 2 to t over 2. Okay? Now, suppose that the Fourier series representation exists, okay? So suppose that the Fourier series representation exists, meaning that we can write x of t, in this form here, okay? So then the question is, how do we find the coefficients ak? Right. So we learned here that we can find the coefficient ak by taking this inner product between x of t and the corresponding complex exponential. Okay? So suppose you start out for the case where k is equal to 0, then a0 is just 1 over t. I can take the integral over any interval of length t, okay? Whichever interval is more convenient for me, I can use. Right? So it doesn't have to be from 0 to capital T. Right? So in our case, in this example here, it's actually more convenient to go from minus t over 2 to t over 2. Okay? Of x of t times e to the minus j 0 omega naught t dt. Okay? So here, k is 0, so I have a 0 in the exponent. So exponential 0 is just 1, right? So I have just an integral over x of t, but x of t is non-zero only from minus t1 to t1, okay? So this becomes 1 over t, limiting the integral from minus t1 to t1, the constant 1 dt, okay? And this gives you 2t1 over capital T. Okay? And you can see that this a0 here is essentially taking the average of our signal x of t over one period. Okay? So this is actually the average value of x of t. Okay. Now, similarly, for k not equal to 0, we have ak equal to 1 over t, t over 2 minus t over 2, x of t, e to the minus jk omega naught t t dt. Okay. So again, this is 1 only from minus t1 to t1. Okay. So I'm essentially just integrating this complex exponential from minus t1 to t1. Okay. So if you work this out, this will give you 1 over minus j k omega naught e to the minus j k omega naught t from t1 to minus t1. Okay? And then you just substitute this inside, right? So you have this term with t1 subtracting this term with minus t1. Okay? So when you have these complex exponentials subtracting each other, you would have a sine function remaining. Okay? Because the cosine part cancels out. So this gives you 2j j k omega naught t sine, oh, sorry, I should have a t here, k omega naught t1. Okay? So I should have a capital T here because of this, right? And this 2j sine comes from subtracting this with t1 and this with minus t1, which is the complex conjugate. Okay? Now here, the j cancels out, right? And by sort of reorganizing the terms, you can write this as 2t1 over t sine 2 pi over t k t1 over 2 pi over t k t1. Okay? So what I'm doing here is just sort of rewriting the terms. So first of all, I'm substituting omega naught with 2 pi over capital T. Right? This is the definition of omega naught, the fundamental frequency. Okay? And here I have, right, j cancels out. Right? I add a T1 here, and therefore I have a T1 here, so that they cancel out. Okay? Let me see. Oh, yeah. And then omega naught is again replaced with 2 pi over capital T. Okay? All right. So here we're basically, replacing these omega naughts with 2 pi over capital T. Okay. All right, now the reason I want to write it in this form is because this is in the form of the so-called sinc function. Okay, so I don't know if you've learned this in other classes, but a sinc function, okay. So a sinc function is defined as sine of x over x, okay? So a sinc function is defined as sine of x over x, okay? Right, so you know that sine is periodic, right? And it is equal to 0 whenever x is an integer multiple of pi, okay? But when x is 0, right, denominator is also 0. So if you apply L'Hopital's rule, right, you need to take the derivative of sine, which becomes cosine, and derivative of x becomes 1. So when x is 0, by L'Hopital's rule, it is equal to 1. Okay, so you would have a function that is equal to 1 at 0, and then you have 0 crossing points at integer multiples of pi. Okay. So your function would look something like this. So the sinc x so you would have a 1 at the origin, okay? And then you have 0 crossing points at integer multiples of pi. Pi, 2 pi, 3 pi, and so on. Okay? So this goes it's not very easy to draw, but see. Something like this. Okay? So you have a peak at 1, and then, so it should cross at pi. I didn't do a good job there. Okay. And then you have 0 crossing points at integer multiples of pi. Okay, so this is minus pi, minus 2 pi, minus 3 pi, and so on. Okay? So this is a sinc function. And you're going to see this quite often in our discussions later on. Okay? Right. So here we're drawing a sinc function with respect to x. Okay. So if you define the sinc function as sine x over x, then what you have here is actually samples of the sinc function, of a scaled sinc function at integer multiples of 2 pi over capital T. Okay? So in this case, you can view this as samples of 2t1 over t sine omega t1 over omega t1 at integer multiples of 2 pi over capital T. Okay? So you're basically, these coefficients AK are obtained by sampling the values of this, sinc function at integer multiples of 2 pi over T. Okay? Now, this is if you view the variable as omega, right, this is the sinc function scaled by T1, okay, scaled by T1. So originally, if you have 0 crossing points at pi, then this means that this sinc function has 0 crossing points at pi over T1. Okay, so assuming T1 is greater than 0, this is like compressing the sinc function. Okay? Okay. So we can try to visualize this. Okay. So if you plot this out, you have 2t1 over t sine of omega t1 over omega t1. Okay. Okay. And the zero crossing points are at integer multiples of pi over t1. Okay. So the peak now is 2t1 over t. And the function is like this.哦，这个电脑有点感测不到。Okay, something like this. Okay. And then, as we mentioned, AK are samples at integer multiples of 2 pi over t. Okay? All right. Now let's first consider the example here where t is equal to 4t1. Okay. So if t is equal to 4t1, then we're sampling at 2 pi over 4t1, which is pi over 2t1 k. Okay. So when t is equal to 4t1, if you substitute this inside, right, 2 cancels out with 4, with 2 remaining, so you have pi over 2t1 k. Okay. So when k is equal to 0, you sample at this point. When k is 0, you sample at this point. When k is 1, you sample at pi over 2t1, which is this point. When k is 2, you sample at this point, right? And then so on and so forth. Okay. So you can sort of, check, right? So this is this sample here. This is this sample here. This is 0, right? 0. This is the negative sample, okay, and so on and so forth. Okay. Now in this second case, we have t equal to 8t1, in which case we are taking samples at pi over 4t1k. Okay. So in that case, k equal to 0 is this sample k equal to 1 is this sample, k equal to 2, 3, 4, and so on. Right, so this is k minus 1, minus 2, minus 3, 4, minus 5, minus 6, minus 7, minus 8, and so on. Okay? So this is for the purple case. Right? So you can also compare, right, to sort of see that this is indeed the case. So this last one is for t equal to 16t1, which corresponds to samples at pi over 8t1k. Okay? So it's difficult for me to continue to draw this, but for this, you're essentially taking, even twice the number of samples than the previous case.